Welcome back. In this video, we're going to look at examples of using the integral test for series. Let's get to it. All right, so here's our first example. We have the sum from n equals 1 to infinity of 1 divided by n plus 7. Now, before you should ever decide to use the integral test, it is important to first try the divergence test for your series. And all that involves is taking the limit as n approaches infinity of the expression in your series. Now, if that limit is equal to a value other than 0, then you know the series diverges. But if it is equal to 0, then the divergence test tells you nothing, and then you need to use another test, like the integral test. And so for all of the examples in this video, the series we are going to be looking at are series that the divergence test is inconclusive for. The limit as n approaches infinity for the expressions in our series will be equal to 0. Okay, so always be sure to use the divergence test first, but if your results are inconclusive, then you can use the integral test like we're going to in this video. Now, in order to use the integral test, what we need to do is look at the corresponding function to our series. And so here's what that looks like for this example. We will have f of x is equal to 1 divided by x plus 7. We have this same expression, but we replaced n with x. And for this function that corresponds to this series, we want to take the integral of this function from 1 to infinity and see if that integral converges. But before we can do that, we need to make sure that this function meets 3 requirements. We need to determine if it is positive, if it's continuous, and if it is decreasing. And all 3 of these things need to be true for the interval from x equals 1 to positive infinity. All right, those are the values of x, or the values of n for our series that we need to check the function for. Right, this series is only defined for n equals 1 to infinity. And so we only need to check that this function meets these 3 requirements for those values. And if we can determine that all 3 of these are true, then we can set up that improper integral and integrate our function from 1 to infinity. All right, and so let's get started. Let's determine if this function is positive to start. And so if you take a look at this function here, are there any values of x for this interval that if we plug them into the function would give us a negative result? Well, if you look at it, we have 1 divided by x plus 7. Now, all the values of x we're working with here are positive values of x from 1 to infinity, and so a positive value plus 7 is always going to be positive. And so you have 1 divided by a positive value, and so this function will always be positive for the values of x from 1 to infinity. And so that checks out. Now let's work on if it's continuous. We need to determine if this function is continuous for these values of x. And so if you look at our function here, what would make this function not continuous? Well, we have a rational function, and a rational function is going to be undefined or not continuous when the denominator is equal to 0. And so if we set that denominator equal to 0, we have x plus 7 is equal to 0, and solve for x, we could subtract 7 from both sides of the equation and have x is equal to negative 7. So when x is negative 7, this function is not continuous. It will be an undefined value because you'd have 0 in the denominator and you can't divide by 0. However, negative 7 is not on the interval that we are working with, right? We are working with positive values of x from 1 to infinity, and so negative 7 is not included on that interval, and so we don't care that this function is not continuous at negative 7. It will be continuous from 1 to infinity. And so we know that our function is continuous on the interval. All right, and so now we have one more question to answer. We need to determine if this function is decreasing on this interval as well. And in order to determine that, we will need to take the derivative of our function. And the reason we need a derivative is because the derivative of a function represents the slope. And so if that derivative is negative for all the values of x on our interval, then we can determine that the slope is a negative, which means that our function is decreasing. All right, so let's take a look at the first derivative here. First, I'm just going to rewrite our function like this. we're going to have x plus 7 to the negative first power. And I just rewrite it like that so that we don't have to use the quotient rule. We can move this quantity to the numerator and give it a negative first power. And now we can just use the chain rule instead. And so if we take the derivative, f prime of x will be equal to the derivative of the outside function times the derivative of the inside function. Now the outside function is the quantity to the power of negative 1, and the inside function is x plus 7. So we'll use the power rule on the outside function. So we'll multiply the negative 1 down, subtract 1 from the exponent, and keep that same inside function. So we'll have negative x plus 7 to the negative second power. And then we need to remember to multiply by the derivative of the inside function, and the derivative of x is 1, and the derivative of 7 is 0, so our derivative is just 1. Okay, so now if we rewrite this, we will have negative 1 divided by x plus 7 squared, right? If we move this quantity with a negative exponent back to the denominator, that exponent becomes positive, and so we're just left with negative 1 in the numerator. All right, and so now looking at our derivative here, can we determine that this will be negative for all values of x from 1 to infinity? Well, if we look at the numerator and denominator separately, in the numerator we have negative 1, that will always be negative, and so the denominator is the only part of this expression that could change the sign of the derivative. And so if we look at the denominator, we have x plus 7 squared, and any value squared will be positive, not to mention that all of our values of x are also positive, and so a positive value plus 7 squared is definitely going to be positive. And so that is not going to change the sign of the derivative. This derivative will be negative for all the values of x on our interval. All right, and so because we know that the derivative will be negative, we can conclude that our function is decreasing on this interval. And so now we have shown that this function, f of x is equal to 1 divided by x plus 7, is positive, continuous, and decreasing on this interval. And so we are allowed to use the integral test by taking the integral of this function from 1 to infinity. And so let's do that. We will have the integral from 1 to infinity of 1 divided by x plus 7 times dx. All right, and so now we can work on solving this improper integral. And if we find that the result is a finite value, meaning that the integral converges, then we can also conclude that our series converges. But if the result of this improper integral diverges, then our series will also diverge. All right, so that's what the integral test allows us to do. And so if I clean up my work here, we can now work on solving this integral. And so the first step is to introduce a limit. Because this is an improper integral, we have an infinite bound. We need to introduce a limit in order to solve it. And so this will be equal to the limit as b approaches infinity, and then we're going to replace infinity with b, and then we'll have 1 divided by x plus 7 times dx. Okay, and so now we can work on integrating this function. And this function can be integrated into the natural log function using the log rule of integration. We have 1 divided by a function that we can set equal to u, and its derivative will also be in this integral, right? So if we set u equal to x plus 7, du dx is equal to 1, because the derivative of x is 1 and the derivative of 7 is 0. And so then if we multiply both sides by dx, we will have that du is equal to dx. All right, now if we rewrite this integral in terms of u, we will have that it's equal to the limit as b approaches infinity of the integral from x equals 1 to x equals b of 1 divided by u du. Okay, so we replaced x plus 7 with u because that's what we set it equal to, and we replaced dx with du because that's what that is equal to. And just note that I wrote my bounds of integration to be x equals so that we remember that our bounds are in terms of x and not in terms of u. So we do need to work back into terms of x after integrating before we can plug in those bounds. All right, so if I continue my work over here, we can now integrate 1 divided by u to be the natural log of the absolute value of u. So this will be equal to the limit as b approaches infinity of the natural log of the absolute value of u evaluated from x equals 1 to x equals b. Now if we replace u with what we set it equal to, which is x plus 7, then this will be equal to the limit as b approaches infinity of the natural log of the absolute value of x plus 7 evaluated from 1 to b. All right, and so now that we are back in terms of x, we can plug in our bounds of integration. We will evaluate this at b and then subtract the evaluation at 1. And so this is equal to the limit as b approaches infinity of the natural log of b plus 7 minus the natural log of 1 plus 7. All right, and I wrote parentheses instead of the absolute value bars because 1 plus 7 is just 8, and that's positive, and b plus 7 will always be positive because we are integrating over an interval where we're only working with positive values. And so we're never going to have a negative result here for b plus 7. Okay, but if you kept the absolute value bars, it's not a huge deal. I just decided to remove them and use parentheses from here on out. And so if we simplify, this is equal to the limit as b approaches infinity of the natural log of b plus 7 minus the natural log of 8. Okay, so now if I clean up my work, let's take the limit as b approaches infinity of both of these terms. The natural log of 8 is just a constant, so the limit of that will just be itself. But if we look at this first term here, what's going to happen to the natural log of b plus 7 as b approaches infinity? Well, if b is increasing and we're adding 7 to it, then that whole expression is increasing towards infinity. And so if that is increasing and we are plugging those values into the natural log function, when you increase the input of the natural log function, or when you input larger and larger values, the natural log function is going to output larger and larger values. And so this whole term is going to approach infinity. And so this is equal to infinity minus the natural log of 8. But the natural log of 8 is pretty insignificant compared to infinity, and so that's still equal to infinity. All right, and so what we find here is that this improper integral diverges, right? The integral is not equal to a finite value, it's equal to infinity. The result is just getting bigger and bigger. Okay, so make sure to write that down, that the integral diverges, and because it diverges, that means that our series also diverges. And so our final answer is that this series diverges. Okay, so that's the final answer, but be sure to write in your own work why this is the case. You want to make that connection between the series and the improper integral. Because this integral diverges, then this series must also diverge because the corresponding function to your series met these three requirements. Okay, so that's what the integral test allows us to do. Let's look at another example. All right, so here's our next example. For this series, we have the sum from n equals 1 to infinity of 1 divided by 3 to the power of n. All right, so if we want to use the integral test here, we first want to find our corresponding function. So that's going to be f of x is equal to 1 divided by 3 to the power of x, right? We just replace n with x, okay? And so for this function, we want to answer three questions. We want to know, is it positive? Is it continuous? And is it decreasing? And of course, we are looking at the interval from 1 to positive infinity. And so if this function meets these three requirements, then we can use the integral test and set up an improper integral for our function. All right, so let's start with if it's positive. If you take a look at our function here, we have 1 divided by 3 to the power of x, and our values of x are from 1 to infinity, and those are all positive values, and so 3 is being raised to a positive value, and so the result of 3 being raised to that power will always be positive. Okay, so no matter what value of x we plug in here, this function is always going to output a positive result. And so we know for a fact that that function is positive. Okay, so now we want to determine if it is continuous. And so if we take a look at our function here, we have 1 divided by 3 to the power of x. This is an exponential function. In fact, we could rewrite it to be 3 to the power of negative x if we move that part to the numerator and make that exponent negative. And exponential functions are continuous everywhere. there's not going to be a value of x for this interval that will make this function undefined. All right, so an exponential function is going to be continuous everywhere, and so we can conclude that this function is continuous for our interval. All right, now we have one more question to answer, and that is to determine if our function is decreasing. So we will need to take a look at the derivative of our function f of x. And so let's take the derivative f prime of x. That will be equal to the derivative of 3 to the power of negative x. Now the derivative of an exponential function, if you don't remember, is equal to that exponential function times the natural log of the base. And then of course in this case we have negative x. This is not just x, and so we need to multiply by the derivative of that exponent, and the derivative of negative x is negative 1, so we also multiply by negative 1. Okay, so that was just the chain rule in action there. We first took the derivative of the outside function, and then we multiplied by the derivative of the inside function. All right, so now if we simplify, this is equal to the negative natural log of 3 divided by 3 to the power of x. Right? We move this 3 with a negative exponent back to the denominator, so the exponent is positive, and then negative 1 times the natural log of 3 is the negative natural log of 3. And so now, if we look at this derivative here, the numerator is always going to be negative, and it's important to note that the natural log of 3 is a positive value itself. If you plug it into your calculator, it's about 1.0986, and so it is a positive value. And so this negative will make that whole value negative. And so the only thing that could change that sign for our derivative is the denominator. But 3 to the power of x is always going to be positive. No matter what power you take 3 to, 3 is going to be positive for this interval. All right? And so this negative will remain unchanged for every value of x for this derivative. And so since the derivative is always negative, we can conclude that our function is decreasing. And so we'll check that off our list. Okay, so now we know for a fact that our function is positive, continuous, and decreasing on this interval, and so we can set up an improper integral and solve it, and use the result of that integral to determine the convergence of our series. So we will have the integral from 1 to positive infinity of 3 to the power of negative x times dx. Okay, and so if I clean up my work here, let's solve this improper integral. We're going to start by introducing a limit because we have this infinite bound, and so this is equal to the limit as b approaches infinity of the integral from 1 to b. We replace infinity with b and take the limit as b approaches infinity, and then the rest stays the same. So we have 3 to the negative power of x dx. All right, and so now we have a fairly simple integral that we can integrate. This is just an exponential function of 3 to the power of negative x. And so if we set u equal to negative x, we can use u substitution and then integrate our exponential function. All right, and so then if we take the derivative of u, du dx will be equal to negative 1 because the derivative of negative x is negative 1. And if we solve for du by multiplying both sides by dx, we will have du is equal to negative dx. Now I don't see a negative dx in our integral, and so then whatever du is equal to should be found within our integral, but I don't see a negative dx, I just see positive dx, so I'm going to multiply both sides by negative 1, and so then negative du will be equal to positive dx, and now we can replace dx with negative du. All right, so if we rewrite our integral in terms of u, this will be equal to the limit as b approaches infinity of the integral from x equals 1 to x equals b of 3 to the power of u times negative du. All right, now if we continue our work over here, we can now integrate this exponential function. And if you don't remember, the integral of an exponential function with a base other than e, such as a to the power of x dx, that is equal to 1 divided by the natural log of a times a to the power of x. Okay, so if we follow that rule in this case, this will be equal to the limit as b approaches infinity of negative, right? We have to keep that negative from negative du, and then we'll have 1 divided by the natural log of the base, which is 3, times 3 to the power of u, and that will be evaluated from x equals 1 to x equals b. Okay? And so now we can simplify a little bit and rewrite this in terms of x. and so this will be equal to the limit as b approaches infinity of negative 3 to the power of u, but u is equal to negative x, so I'll have negative 3 to the power of negative x divided by the natural log of 3 evaluated from 1 to b. Okay, now if we move 3 to the power of negative x back to the denominator so that the exponent is positive, then this will be equal to the limit as b approaches infinity of negative 1 divided by 3 to the power of x times the natural log of 3 evaluated from 1 to b. Okay, and so now we are ready to evaluate this expression at b and subtract the evaluation at 1 and then evaluate our limit. And so if I clean up my work here, if we evaluate at our bounds, this will be equal to the limit as b approaches infinity of negative 1 divided by 3 to the power of b times the natural log of 3 minus negative 1 divided by 3 to the first power times the natural log of 3. Okay, so we plugged in b and then we subtracted plugging in 1. And so now I'm going to continue my work up here again. If we simplify, this is equal to the limit as b approaches infinity of negative 1 divided by 3 to the power of b times the natural log of 3 plus, right, these two negatives will cancel out to become positive, 1 divided by 3 times the natural log of 3. Okay, so now the limit as b approaches infinity of this term, which is a constant, will just be that value. But what about this term? What happens to the value of this term as b approaches infinity? Well, as b gets greater, 3 is being raised to a higher and higher power. And when you raise 3 to a higher and higher power, that value will get larger and larger. So we have infinity times the natural log of 3, which is still infinity. And so we have negative 1 divided by infinity. Or you could also view it as negative 1 divided by a denominator that is increasing. And when you have a fixed value divided by infinity, or an increasing value, that is going to become 0. Okay, so as b approaches infinity, this term approaches 0. And so this is equal to 0 plus 1 divided by 3 times the natural log of 3. And that's just going to be equal to 1 divided by 3 times the natural log of 3. And so this improper integral is equal to a finite value. This improper integral converges. And so we can write that down. This converges. And since it converges, we can conclude that our series also converges. And so we'll say that this series converges. Okay? And so that is the final answer to this example. Because we could show that the function that corresponds to our series is positive, continuous, and decreasing, then we could look at the improper integral from 1 to infinity of that function, and since that converged, we now know that this series will also converge. All right, let's look at one more example for this video. All right, so here's our last example. We have the sum from n equals 1 to infinity of n divided by 4 times n squared plus 9. And so if we want to determine if this series diverges or converges, we would originally start with the divergence test, but that would give us an inconclusive result. And so now we can try to use the integral test. All right, and so our first step is to look at the corresponding function, f of x, and that will be equal to x divided by 4x squared plus 9. We just replaced each n with x. And now for this function, we want to answer the following questions. Is it positive? Is it continuous? And is it decreasing? And we will be answering those questions for the values of x on the interval from 1 to infinity, right? This corresponds to the values for our series of n from n equals 1 to infinity. All right, and so let's start with the first question. Is this function positive? And so if you look at this function, in the numerator we have just x, but remember, x can only be positive values from 1 to infinity, and so the numerator is always going to be positive. And in the denominator, we have 4 times x squared, and x can only be a positive value, and so if we're squaring it, that's always going to be positive. And then we're just adding 9, we're not subtracting anything, and so this denominator will always be positive. This function is going to be positive for all the values of x on our interval. And so we can check that off and move on to our next question. Is this function continuous everywhere for this interval? And so if we look at our function here, it is a rational function. And so the only way that this will be not continuous or undefined is if the denominator is equal to 0, because we can't divide by 0. And so if we set the denominator equal to 0, 4x squared plus 9 is equal to 0, and solve for x, that will tell us what values of x this function will not be defined for. And so if we subtract 9 from both sides of the equation, we will have 4x squared is equal to negative 9. And then if we divide both sides by 4, that will give us x squared is equal to negative 9 divided by 4. And if we take the square root of both sides, we would be taking the square root of a negative value, which would give us an imaginary result. And so we can conclude that there are no real values of x for which this function will be undefined for. And so no matter what value of x we plug in on this interval from 1 to infinity, this function will be continuous. There are no discontinuities on that interval. And so we can check off that question. And now finally, we want to determine if our function is decreasing on this interval. And so what we can do is look at the first derivative of our function. Now in this case, it looks like we will need to use the quotient rule, or at least that's what I'm going to use. And so if you don't quite remember the quotient rule, I'll have it up here on the screen for you to reference. But if we go through that, f prime of x will be equal to the following rational expression. We'll have the denominator 4x squared plus 9 times the derivative of the numerator. And so the derivative of x is just 1, so we multiply by 1, and then we will subtract the numerator, x, and multiply it by the derivative of the denominator. Now the derivative of 4x squared will be 8x if we multiply the exponent down and then subtract 1 from the exponent. So we multiply by 8x, and the derivative of 9 is 0, so we just have 8x. Okay, and so then the denominator will just be the original denominator squared. And so we will have 4x squared plus 9 squared. All right, now if we simplify, this will be equal to 4x squared plus 9 minus 8x squared divided by 4x squared plus 9 squared. Now we have two like terms in the numerator here, 4x squared and negative 8x squared, 4x squared and negative 8x squared. If we combine those, we will have negative 4x squared. And so if I just rewrite this, we will have negative 4x squared plus 9. So negative 4x squared plus 9. Okay, and so that is going to be our first derivative. And so by looking at our first derivative, can we conclude that this will always be negative for all the values on this interval? Well, to start, we know that the denominator is always going to be positive because we are squaring the value of x and then squaring the whole denominator. So no matter what value of x we plug in down here, this denominator is always going to be positive. So that's not going to change the sign of our derivative. The only thing that can affect the sign is the numerator. And so this is a little bit tricky. It's not entirely clear what values of x will keep this numerator negative. And so what we will do is we will look at the numerator, negative 4x squared plus 9, and see what values of x would make that expression less than 0. In other words, what values of x make this expression negative. And so if we solve for x, let's start by adding 4x squared to both sides of the inequality. We'll have 9 is less than 4x squared. And now dividing both sides by 4, we will have 9/4 is less than x squared. And then if we take the square root of both sides, and I'm going to write this step up here, we will find that x is greater than 3/2. Now what this means is that when x is greater than 3/2, our derivative will be negative, which means the function is decreasing. All right, now 3/2 is equal to 1.5. So if I rewrite that, we have 1.5. 1.5 is greater than 1. So our function is not decreasing for the entirety of this interval. It starts decreasing after 1.5 and not for this entire interval from 1 to infinity. From 1 to 1.5, our function will not be decreasing. And so it seems like we will not be able to use the integral test here. However, we can make an adjustment so that we can use the integral test. What we can do is actually change the interval that we are working with. And so here's why that's the case. For a series that we want to determine the convergence of that series is not going to be changed by removing some of the terms from the beginning of that series, right? If this series starts at n equals 2 or n equals 3, the convergence of this series is not going to change because the convergence is what is happening over the long term for that series. So it's not going to be affected by the first couple terms. What will be affected if this starts at n equals 2 or n equals 3 is the actual value of the sum. But we're not really worried about that in this problem. We're just using the integral test to determine if the series converges. And so what we can do is just remove that first term of n equals 1 and look at the values of n after that, or the values of x after that, where it is decreasing. And so since we're only looking at integers for a series, right, we look at n equals 1, then n equals 2, then 3, and so on. We don't want to look at the interval from 1.5 to infinity, so we're going to round up and look at the values from 2 to infinity. And so we'll write in 2. Okay, and so really what we are now looking at is the convergence of this series from n equals 2 to infinity of n divided by 4n squared plus 9. But the convergence of this series will be the same as our original series. It doesn't matter that we're cutting out that first term. The convergence will remain the same. All right, and so we can say that our series is decreasing on this interval from 2 to infinity. So this derivative will be negative for values of x starting at 2 to positive infinity. And so we can check off that last question. We did have to make a slight adjustment, but we will still be able to use the integral test regardless to determine the convergence of our original series. Okay, and so now that we have determined that our function meets those 3 requirements, we can set up our improper integral. Now remember, we are working with a different interval now. When we set up our integral, we are now going to have the integral from 2 to infinity of our function instead of 1 to infinity. And so then we'll have our function x divided by 4x squared plus 9 times dx. Okay, so when you make an adjustment to the values of x that you're working with, be sure to use that new lower bound for your integral. All right, and now I'll clean up my work and then we can solve this improper integral. All right, now our first step is going to be to introduce a limit to take care of this infinite bound. And so this will be equal to the limit as b approaches infinity of the integral from 2 to b. We replace infinity with b and then have the limit as b approaches infinity, and then everything else is the same. So we have x divided by 4x squared plus 9 dx. Okay, and so now how can we integrate this integral? Well, it looks like we have a function and its derivative, right? We have an x squared function in the denominator, and it's just being added to a constant, and so the derivative of that denominator will be x to the first power. It'll be multiplied by some constant, but we're not worried about the constants. We're just worried about the powers of x matching up, right? So if we set u equal to 4x squared plus 9, the derivative du dx will be equal to 2 multiplied down and then subtract 1 from the exponent. So we'll have 8x, and then the derivative of 9 is 0. So the derivative of the denominator is 8x, and if we solve for du, we'll have du is equal to 8x dx, and since I just see an x dx in our integral, not an 8x dx, we can divide both sides by 8, and we'll have du divided by 8 is equal to x dx. Okay, and so now we can use u substitution to rewrite this integral and then integrate. And it's going to be in the form that we can integrate with the log rule of integration. And so you'll see that, but let's write it out. This will be equal to the limit as b approaches infinity of the integral from x equals 2 to x equals b of 1 divided by u times du divided by 8. Okay, so we replaced 4x squared plus 9 with u, because that's what we set it equal to, and we replaced x dx with du divided by 8, because that is what that is equal to. And so now if we continue our work over here, this will be equal to the limit as b approaches infinity of this integral, but if I pull this 1/8 out to the front, we will have 1/8 times the integral from x equals 2 to x equals b of 1 divided by u du, and the integral of 1 divided by u is equal to the natural log of the absolute value of u. And so this is equal to the limit as b approaches infinity of 1/8 times the natural log of the absolute value of u evaluated from x equals 2 to x equals b. All right, now if we replace u with what we set it equal to, which is 4x squared plus 9, then we will be back in terms of x. And so this will be equal to the limit as b approaches infinity of 1/8 times the natural log of the absolute value of 4x squared plus 9 evaluated from 2 to b. Okay, so now if I clean up my work here, we can evaluate this expression at b and subtract the evaluation at 2. So this will be equal to the limit as b approaches infinity of 1/8 times the natural log. And I'm not going to use these absolute value bars because 4x squared plus 9 is always going to be positive for both b and 2, because b is only going to be positive values of x, and 2 is a positive value. So we'll have the natural log of 4 times b squared plus 9 minus the natural log of 4 times 2 squared plus 9. All right, now 2 squared is 4, times 4 is 16, plus 9 is 25. So this is just the natural log of 25. So we'll rewrite that. And now let's take a look at the limit as b approaches infinity for both of these terms. The natural log of 25 is just going to be the natural log of 25 because the limit of a constant is equal to that constant. But what about this term here? Well, as b approaches infinity, we have b squared. So we have an increasing value that is being squared. So that's going to continue to increase. Then we're multiplying it by 4, so it's still increasing. We still have an increasing value. And then we're adding it to 9, so it's still increasing. It's still infinity. And so as you input a larger and larger value into the natural log function, it's going to output a larger and larger value. And so it's going to approach infinity. And so this will be equal to 1/8 times infinity minus the natural log of 25. But infinity minus the natural log of 25 is still going to be infinity, and infinity times 1/8 is also still infinity. And so our improper integral is equal to infinity, which means it diverges. All right, infinity is not a finite value, it's infinity, and so that means that our integral does not converge to a specific value, it diverges. And so because this improper integral diverges, we can conclude that this series diverges as well, which means that this series diverges too. All right, and so our final answer is that our series diverges. Okay, so that is the final solution. And be sure to make that connection between the improper integral and your series when you write down that answer in your work. Be sure to say that this series only diverges because this improper integral diverges as well. Okay, and so with that, this was the last example for this video. So if you have any questions, leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.